Good afternoon, everybody, and welcome to the Center for Policy Research. I'm Radhika Khosla, and we're delighted to have all of you here, and also delighted to have with us this week Professor Grubler, who's here visiting. For those of you who don't know him already, he's a globally renowned expert on energy transitions and demand-side approaches, and so we feel very fortunate to have him here for a whole week visiting at CPR, and of the many things that he's doing while he's here, along with speaking with us today, is holding a 3-day seminar course for scholars from around the country, and also having a number of other individual meetings. And the point of this whole sort of series is to be able to say that are there ways in which we can take the demand side of Indian energy more seriously, and what would it take to get there. So as part of those many, as part of sort of moving towards that end, one of the things that he's doing is giving this first public lecture. And just to give a little bit more on his background, so Professor Grubler his research focuses on the long-term history and future of technology and the environment, with an emphasis on energy, transport, and communication systems. He's currently based at IASA in Austria and has also held an appointment at Yale. He's a widely published author and has been an active part of the IPCC since '96, including as lead author. And he served as the convening lead and coordinating author for 3 knowledge modules: Urban Innovation and Energy Systems of the Global Energy Assessment. So today, Arnav is going to speak with us about an end use and energy efficiency strategy for sustainable development with climate change mitigation as an entry point. And I won't speak more about the talk because Arnav also asked me to keep it brief. So we'll just hand it over to him, and once again thank him for being here with us, and also to all of you for being here. So over to you.
Thank you very much, Radhika. Well, thank you all for coming. Thank you for the invitation to visit India. And, okay, I need my timer clock. Thank you very much. It's a pleasure to be here, and I look forward to numerous opportunities for exchange, not only after this seminar in the discussion, which will not be recorded, so we can discuss intellectually freely and openly. But also during the week, I have arranged with Radhika some office hours in the afternoon, so we'll be available and just sit in the office and wait for any drop-in and come with any question or any passion you have. It's difficult to start a talk where climate change is in the topic in a country like India. We all know it is a very charged topic. And that's why I put this button on. I wear it on all of my talks. It symbolizes the 17 SDGs from the UN, so these 17 colors. It's a nice symbol, and that's also the main entry point of the talk. It is to try to reframe the linkage between sustainable development and climate change, where we no longer speak of the sustainable development co-benefits of climate change, but rather speak of the climate protection co-benefits of sustainable development. So it's a slightly different slant on the problem. And the perspective that allows us to reframe it is a perspective on energy end use and efficiency. Not only energy, but also generally resource use. So why I'm proposing this end use and efficiency strategy? Well, when we look at our systems, all systems have a demand component. It's food or water or energy or communication or transportation services. And then we have a supply component. And what is common amongst these systems is that the largest interaction these systems have with our societies and economy is actually at the point of end use. Here we have the largest employment effects of investments. We have the largest effects on efficiency gains. And we also have the largest SDG co-benefits. The reason is very simple, because we affect many people. If we improve something, a new technology, a service provision, higher efficiency, we affect the livelihoods of many more people. If we improve on power plant, that's great. and the benefit accrues indirectly to people, but because these are very large-scale technologies, they are very capital-intensive. As a result, they're very labor-extensive and also very sustainable development extensive. But there are very few sustainable development co-benefits if we work from the centralized supply side. An important interlinkage between the demand and the supply side is that the lower the energy demand, the more flexibility and resilience you have upstream on the supply side. If the demand is high, you need all options at 100%, at the maximum. And if one option fails, you have already a problem. If the demand is low, you have choices, freedom of choice. You have tolerance to innovation failure, which is inevitable in any technological innovation. So therefore, also the supply side needs to be interested in energy efficiency and demand, because the lower the demand, the easier and the more resilient the supply side is. And at the level of the demand side, we can use much more certain options than others. And here comes now a mouthful of different buzzwords. I apologize for it, okay? But this is the discourse in the technological innovation literature. That's where the action happens. That's where we have rapid progress. We do not have rapid progress on the supply side. Everybody talks about fusion energies. For 50 years, we talk about fusion power. We are not having fusion power. Everybody talks about solar satellites, you know, where we beam with microwave radiation electricity from solar satellites onto the Earth. We talk about this for 30 years. I haven't seen a single satellite yet doing it, okay? But we see rapid progress in end-use technologies, and this is basically a progress in granular options. Granularity is a term which we have coined in the Global Energy Assessment Innovation chapter. It refers to technologies which have small unit scales. So this is the perfect example of a granular technology, and the opposite of a lumpy technology is the aircraft I used in landing here in New Delhi. It was an Airbus 380. It's a nightmare. You know, if you have 1,000 people bunched in an aircraft, loading and unloading of the aircraft becomes a for real problem, and that's the disadvantage of lumpiness. We can talk about much more emphasis on distributed systems that are easier to build and more resilient. We can talk about the benefits of economies of scope as opposed to the traditional benefits of economies of scale. These are buzzwords like sharing or circular economy. And finally, we can also talk about people and how people interact, because people and how they interact are important determinant of the speed of adoption of novel technological solutions. And this is of essence. Speed is of essence. We have discussed too long, we had too many meetings, we had already too many COPs, and we have too little impact, and that's not only in the climate change agenda, but certainly also in the sustainable development agenda. We need rapid action rather sooner than later, and understanding how we can harness the power of people and social networks in accelerating transitions to sustainable development is much more interesting than yammering and complaining about the lumpiness and inflexibilities of our large-scale centralized supply infrastructures. So let me give you a couple of illustrations on how efficient are our systems actually. Now in the energy field, this is easy because we can use the concept of exergy or availability. So on the top panel, you have an exergy efficiency cascade. How much of 100% primary exergy available in the system ends up as final exergy, so that's the exergetic equivalent of final energy. How much ends up as useful exergy, and finally we also use the exergy calculus. It's almost a calculation of the actual realized efficiency in comparison to the thermodynamic possible. So we use that also for service efficiency. So let's say a car with a load factor of 20% only, of course, has a theoretical exergetic service efficiency improvement potential of having a load factor of 100%. So having the car full instead of a single person in the car. this is important because load factors, the way how we use the technology in many cases is more powerful and influential on the efficiency of the device than actually the device itself. Many years ago, I used data from Terry on urban mobility in Delhi, and I always use this data in talks in Europe or in the US because you can show that actually the load factor of bicycles in Delhi, 1.3 people per bicycle, is actually higher than the load factor of cars in the US or in Europe, 1.2 people per car. So we can do the same kind of calculus for water. So this gives you the same efficiency cascade, how much of the original available water ends up in crops. So this is basically irrigation efficiency times the efficiency of water assimilation by crops. How much of that water representing the crop, embedded in crop, ends up in food. So this is basically upstream supply losses, for instance, in large-scale storage. And finally, how much of that food ends up in nutrition. Now, this might be something you might be surprised from an Indian perspective, but this is the reality in all cities of the developed countries. In a city like Vienna, you will be surprised to hear that 50% of the food sold in supermarkets ends up in the dump. It's food waste. Actually, 80% of that food waste is in original packaging, has not even been opened. So people buy things in the supermarket, don't even open it, and then throw it away. So talking about efficiency of water in irrigation certainly is important, but talking about water efficiency by minimizing food waste is even more important because you have the compound effect of all of the conversion efficiency losses through the chain that is dictated by the end-use efficiency of water. So we have a recurrent story. It's not a story of energy, it's a story of water, it's a story of food, it's a story of raw materials. The end-use efficiency is an important leverage and entry point. For end-use efficiency, I show you what does it mean if you translate any improvements. So here is a simple thought experiment based on actual statistics. Let's say you have an end-use application like lighting in India. If you improve the lighting efficiency by 1 exajoule across all of India, then how much primary energy can you save? And the answer is 85 exajoules. So for each unit of energy you save in introducing an LED light bulb in India, for each of this unit of energy you save 85% of primary energy. That's basically the whole input into the electricity power plant that actually provides the electricity to the light bulb. For the world, this number is 40. In the US, the number is 25. For transportation, we have similar leverage effects, not factor 80, but let's say in India, we still have a factor of 8 in the leverage effect. So that means for each unit of energy we save in transportation, we save 8 units of crude oil being extracted from Mother Earth. So this shows you how powerful anything that happens in end use is. Often we think it's marginal. Okay, per light bulb we save only a small amount, but aggregated over the entire economy we save big, and we save even bigger upstream in the primary energy which we save to supply. Obviously there are dynamic feedbacks, we need to understand these feedbacks, often referred to as takeback effects, but the basic fact is there is an important upstream leverage effect. This is based on the work of my colleagues headed by Kevan Riahi at YASA that did the scenarios for the global energy assessment, and I just show you here 2 scenarios. The heading do not appear. On the top you have the GEA energy efficiency scenario. So you see the gray wedge on the top, that's the energy that is conserved compared to the baseline. So that's the efficiency scenario. And on the bottom you have the energy GEA supply scenario where the efficiency improvement is relatively modest. Now what's the implication of this on the supply side? They have analyzed this by so-called technology knock-off scenarios. So these are scenarios in which you assume that one option is not available. for instance, nuclear, is not available. It doesn't work. Or CCS, carbon capture and sequestration, doesn't work. It's knocked off. You have limits on bioenergy. You have limits on this and that. So 40 different scenarios of knockoff. And you have this for two different groups of scenarios. One scenario that assumes advanced transportation technologies, so something what we talk about, car sharing, electric cars, fuel cell vehicles. And the other one in which the transportation sector doesn't innovate. We basically are stuck with conventional transportation technologies. Now, the interesting thing is how densely populated the efficiency scenario space is. So for this scenario, all knockoff scenarios work. So that means we can supply that energy despite we have excluded a certain technological option. It produces structural change, as you see on the different stacks. But the most important message is to see how densely depopulated space is on the top and how sparsely populated it is on the bottom, particularly in the conventional transportation scenarios. There, only two scenarios are feasible anymore. So that means in scenarios where the demand is high, you have very little tolerance for innovation failure. You have to make sure that all technological options that are needed actually work. As a student of technology history, I can only wish you good luck. This is an illusion of the engineers that they can make a technology work. If a technology is not acceptable at a social level, or if a technology is simply not economic or cannot be made economic, then that technology will not work. And it has happened and will continue to happen. Not every whiz kit and fancy technology that is around the corner will work, and we need to think about how can we make our systems work if things fail. And things will fail. That's the only certainty which we have in this system. We also have to accept that we live in a very dynamic age in which things change. Now, we are all familiar with technological change, and we are enthusiastic about it, including myself. But we often tend to forget that also our societies change. And it is this dimension of social change which we need also to capture. Two very important trends are emerging, particularly in the OECD countries. I cannot speak for India. I have not studied it for India. The first trend is a persistent change in diets. The OECD countries are moving to a diet which you are very familiar with, as a very selective use of meat, focus on high quality, chicken normally not very high quality, fish high quality, and a significant reduction in red meat consumption. Even in countries like the US, for instance, red meat consumption in the US peaked in 1965 at 60 kilograms per capita and is now below 40 kilograms per capita. So this is a trend occurring in all of the OECD countries. A second important change I'll illustrate in a second is that new generations, the young people, defy materialism. The emphasis is on the use of artifacts and no longer on the ownership of the artifacts. No artifact has been as charged symbolically as the private vehicle, the car, and the car has fallen out of fashion amongst the young. I'll illustrate that in a second. We have new business models, and these business models cater to these new technological and new lifestyle opportunities of our economy. We have rapid progress in pervasive digitalization and ICT convergence. This is just one of the many symbols, but we have this rapid progress and we can harness it to bring these new business models alive. And as a result, we have rapid innovation in granular technologies and integrated digital services. What this could mean, I'll illustrate in a second, but first let's review some of the trends. Now this is, I apologize, this is very pedestrian. This is an illustration of one of my classes in the US, because these are Yaleys, so these students come all from very affluent families and they have no idea what actually efficiency and end use means, because they take privilege and luxury as a birthright. Now this gives you three vehicles with vastly different energy efficiencies. A Toyota Prius, 50 miles per gallon, apologies for the US metric here. Cadillac Escalade, which is the most guzzling SUV, 15 miles a gallon, and finally a good old diesel school bus that has even less energy efficiency, only 8 miles per gallon, so very lousy energy efficiency. The difference in the service efficiency comes from the different load factors. Typically in a zip car, this is a car rental system in the US, there's one student or one professor sitting in there. So Arnulf would typically sit in a zip car, and that ends up with an energy per unit of service of 1.5 megajoules per passenger kilometer traveled. In the SUV, mostly used for family chores, so the term used in the US is a soccer mom that transports school children to soccer games, and that's why she's called the soccer mom. So mommy has at least 3 kids in her SUV, and because there are 4 people sitting in the car, it's actually already more energy efficient per passenger kilometer transported than the super energy efficient Prius. And lo and behold, the good old inefficient school bus beats all other technological configurations. So we have the irony that the least efficient technology provides the most efficient service because the load factor is the highest. So, basic conclusion, the way how we use the technology is more important than the technological efficiency of the artifact itself. So do not forget the user when you talk about the efficiency. The user can amplify the efficiency, enhance the efficiency of an artifact, but the user can also nihilate the efficiency improvement of a new artifact. This can be more than 100% take-back effects. Through changes in behavior, efficiency improvement potentials might not be realized at all. So that's why we need to understand the user and the patterns of behavior. So this is the trends. So there's a lot of numbers. So lo and behold, let's just look at the aggregates. Whatever is in the left indicates countries and periods and age cohorts in which the percentage of young people having a driver's license has decreased. The most important and pronounced example is Sweden. In the age category up to 19 years, now only half of the young people actually have a driver's license. We have a province in Austria, close to the Swiss border, Vorarlberg, where the percentage is now also below 50%. So every second young person no longer wants to have a driver's license. You will be surprised that this trend also exists in the US, and this is a trend persistent for quite some time already and across all age groups. So not only the young people are renouncing car driving and driver's licenses, but also older age groups. Of course, the trends are less dramatic compared to Sweden or some provinces in Austria, so there typically only 3/4 of the population have a driver's license. And then you have here the sample of the countries and age cohorts which still have increasing car driver's licenses rates. I would presume that the young people in India are still in this category, but I do not have the data to prove it. But the important point is that this sample basically includes many countries that also appear in the other sample. So see, up to 2010 in Austria, we had increasing car driver's licenses. And ever since 2010, Austria too, actually we have now a decrease. So we have a trend break. So we have a trend break, and the trend break and the recent trends suggest that the traditional model of coming of age, first you make a driver's license, and then grandma and grandpa buy you a car, is no longer valid. Not only people don't want to own a car, people even don't want to drive it anymore. What's the reason? Well, for the car supply side, it's definitively Uber, but on the other side, it is the significant progress we have made in public transportation in all major cities in the developing countries, simply because of environmental, climate change, and urban functionality concerns. I mean, if I look at the traffic congestion in Shanghai or here in New Delhi, I have to say that functionality of urban transport systems require urgently a much larger emphasis on public transport, because that's the only technology which we know by which we can move lots of people at the same time. A car is a great technology for disperse and rural, low-density applications, but it's a very, very bad technology in dense urban environments where we need to move masses. That means millions of people every day. So, social change. Technological change. This is an illustration of the impact of ICT convergence. So on the left hand, you have an iPhone. Typically, an iPhone has a peak power demand of 5 watts and a typical energy use of 2.2 watts. We measure here standby. This is a database developed by LBL in Berkeley to review empirically all consumer devices. On the middle part, you have little icons. These are all services your iPhone now provides and which traditionally were provided by separate artifacts. So you had a record player, you had a cassette recorder, you had a dictaphone, you had a fax machine, you had a TV, name it. All of these functionalities are no longer provided by separate artifacts, but by an integrated digital platform, which is represented here. And if you do the math, if you add up all of the peak power use of these artifacts, you add up to 550 watts and a standby energy use of 72 watts. So by dissing all of these individual artifacts and converging them into a digital integrated platform, you actually have an improvement in peak power demand of a factor of 100 and an improvement in standby energy consumption of a factor of 30. So that's a very powerful illustration of actually the potential of energy conservation and resource conservation by converging different services that were traditionally provided separately into one integrated thing. That's, of course, an extreme example, but we can think of other examples as well. Think about all of the discussion of electric mobility. Now, electric cars of the future, or even of today, if I think of the latest Nissan Leaf, will no longer be electric cars for mobility. These will also be energy storage and energy generation platforms. The Nissan Leaf is already ready for vehicle to grid, so you can actually connect the car to your domestic grid, or even sell it if you find an appropriate aggregator, like a retail utility, like OVO, that's a German company that offers this business model in Europe, into the grid. But for the time being, rather feed it into your domestic grid, and I'm surprised that not a lot of people are talking about this in India, where I read about chronic electricity blackouts, and everybody has a diesel generator in the basement. So instead of a diesel generator, why not use your electric car as an electric backup system? And with 40 kilowatt hours, a typical household can go for a week with the electricity stored in a car. So that's actually a lot of electricity to be used as a backup source. So, granularity. So this is, again, a class illustration of the concept of granularity between large-scale unit size. These are indivisible projects, so you either buy an entire aircraft, but you cannot buy half of an aircraft. And because they are large and capital intensive, they involve high financial risks. So it's very difficult to find funding. That's the crux of nuclear power. Anywhere where you have deregulated markets, you don't find anybody who is prepared to cough 10 billion euros for a nuclear power station. In centrally planned markets or completely centralized and regulated markets, this still might be possible. I cannot judge on India, but in some countries like South Korea, it's still possible to fund nuclear power, but in the US and in Europe, it's impossible to fund it, simply because the investment required is so big and the financial risk is so high that private capital doesn't want to touch it. Everybody says the government should do it. So the usual thing, Governments are supposed not to pick winners, but the private sector dumps the innovation lemons onto the government, so the government should do it. We can go down then from the medium scale, a car or wind turbine, to a smaller scale, a bicycle or a PV panel, all the way to a cell phone or a light bulb as the most granular technology. Now, as we move down this hierarchy, the size gets smaller, so we need many more of these units to satisfy a given demand. So that means we need to manufacture more of these units. And as we manufacture more of these units, we do more experiments with them, and we have opportunities to improve the technology. Let's say, if you build 2 billion cell phones, you have a lot of possibilities of innovation compared to if you build 2 nuclear power plants. There are not a lot of possibilities of innovation. And because these are modular, scalable technologies, they can be much more easily ramped up, and each of them represents a low financial risk. If the technology doesn't work, how much do you lose? Okay, if a wind turbine doesn't work, you lose $2 million. Okay, it's not peanuts, but it's acceptable. And if you're not happy with your iPhone, well, okay, each kid in Europe will go to its iPhone provider and say, I want to have it changed over. The average lifetime of an iPhone actually in Europe is now about approximately 6 to 8 months. That's the rapid innovation cycles which this industry has dictated. Now, of course, we can criticize it. That means a lot of electronic waste to be recycled. But let's not forget the downside or the upside of rapid life cycles is each time we have a new generation, we can add a lot of technological and service functionalities to it. So short life cycles are actually very good for innovation because you can introduce a lot of innovations. There is an environmental penalty which we should not forget. There's another one, and this brings us to the sustainable development context. There's another advantage of granularity is that granular technologies reach more people. So these are global Lorenz curves. I'm pretty sure I don't need to explain Lorenz curves like I usually would have to do it to my students. So basically, we just show the inequity of access to certain technologies. So let's take the most extreme example of inequity. That's actually broadband internet access in 2014. You see that 90% of the world population do not have access to broadband internet access, and the resulting Gini coefficient of 0.89 suggests an extreme high inequity. We have a second technology which is as inequitably distributed, and that's the cell phone in the year 2000. So in the year 2000, the cell phone globally was inequitably distributed as broadband internet is today, but the cell phone today is here. Today, the cell phone is the most democratic technology on the planet. It used to be the radio and the bicycle, but the cell phone even has outcompeted the radio and the bicycle. Radios are here, and bicycles are here. And quite, you see, surprising, the bicycle is not that democratic as we would see. 40% of the world population does not own or does not have access to a bicycle. The reason is not necessarily economic, but functionally, lack of road infrastructures, and above all, social and culturally. For instance, in many countries, women are not supposed to ride bicycles, and that, of course, excludes half of the population from access to this technology. So, the more granular technology is, the more easier we can bring it to everybody on the planet. And I think this is an important equity dimension which we frequently forget in the sustainable development discourse. Now, how do we weave all of these trends together? I mean, this was all scattered and preaching to the choir. Now, we have done over this last summer at YASA a kind of crazy experiment. We tried to develop a new global integrated scenario within 3 months with all the bells and whistles of our integrated assessment modeling framework. So it was a challenge, but we were successful. I don't know whether the publication will be successful, how it will feature in Nature. We are still in the review process, but we will see. The point was to develop a scenario of rapid transition. Slow transition scenarios we have plenty. That's not the issue. But we have very few scenarios of rapid transitions. And based on the logic and thinking I've presented earlier, the idea was we can achieve these rapid transitions only through an end-use strategy that focuses on efficiency and on granular, distributed, scalable options. These options can change potentially very, very fast. Okay? By changing end use and the technologies in end use, we force the upstream sector to change as well. The traditional model is we need to force the utilities to change, the energy supply. Here, the consumer forces, the changing preferences of the consumer forces the utilities in the supply sectors to change. And as overall narrative and integrative driver, we've picked not necessarily climate change, also it is an important research topic, but the overarching research narrative focuses on the SDGs. That means it has a much broader base than simply climate protection. So that's the lead scenario I illustrated here with some kind of stylized diagrams on emissions. So that's the traditional scenarios which many of you have reviewed and which are numerous and proliferate in the literature. The narrative is we have large inertia of the system, we have huge development needs in developing countries, and as such, there's very little which we can do on climate change mitigation, so emissions continue to rise rapidly. In order to manage climate change, then at some point in the future, typically 2050, we need a precipitous decline, and this overshoot of emissions is compensated in the long run by so-called negative emission technologies. That's basically taking CO2 out of the atmosphere. Classical example, use biomass, okay? Biomass takes CO2 out of the atmosphere, and then you burn the biomass in conjunction with carbon capture and sequestration, and you geologically store the CO2. So that's a classical negative emission technology, and it's the dominant technology in all integrated assessment model runs of climate scenarios of 2 degrees or even lower. This is a different scenario. Here we have no inertia, we have rapid change because we change those components of the system that can change the most rapidly. Behavior, end use, granular end use technologies with rapid innovation cycles and short lifetimes. These granular distributed options at the end use have spillover effects on the supply side. Whatever we do on the end use has an important implication. If people install PV panels and the PV panels become cheap, all of a sudden utility scale PV systems also become cheap. And so that's the motivation. And as such, these end use innovations lead the way and drive the supply side transformation. Because the demand is low, these innovations can lead to rapid change also on the supply side. If the demand grows, any innovation you add on the supply side will produce a small impact on the supply structure. If the demand is low, any innovation you add produces a huge impact. And instead of negative emissions, we have formulated, okay, it's wishful thinking perhaps, a scenario of grand restoration, in which efficiency and high productivity in agriculture, changes in diet, high efficiency agriculture and food systems, allows us to return land to nature, to restore the perturbations on the ecological cycles and ecosystems we have inflicted, and as such have a co-benefit in sink enhancements, that means in CO2 absorption, which is not the main objective. The main objective is biodiversity conservation and conservation in general, but the side benefit is sink enhancements.
Just a quick clarification. Vertical axis is emissions.
This is emissions, yes.
Why does it rise in the second one?
And there's always a short-term rise over the next 10 years because we started the simulations in the year 2020. We didn't want to impose an emission decline in the year 2010 because this would be counterfactual. Okay, so there's a short-term increase, and even in this rapid transformation scenario, you have some perturbation, inertia in the system. Not everything. We're not going to throw away every tuk-tuk here in New Delhi immediately. You know, we'll give it a grace period of 2 or 3 years and before it will be replaced by an electric tuk-tuk, okay, so under this scenario. So there is some kind of transition time also required here. This is the way how we have integrated the SDG narrative. We have looked at one SDG in particular, and that's SDG 12, which is normally a little bit fuzzy, and so nobody wants to talk about it. Nobody has any idea what does it mean to have responsible production and consumption. Okay, we have taken the challenge and looked at all of the other SDGs. What is the bearing on SDG 12? And the commonality across all of these SDGs is actually how efficient you use the resource. Are you wasteful or are you not wasteful? And that's a critical component in ending poverty. It's a critical component in ending hunger. It's a critical component in industry, decent work and economic growth, etc. So, SDG 12 basically, through this end use and efficiency focus, addresses 12 of the 17 SDGs. It's a simple one, okay, not everything is efficiency, we understand that, but it's nice to have at least one integrative narrative and trend across so many different SDGs, and that integrative component is efficiency. Use resources exceedingly sparingly. Okay, but we don't want to use resources only sparingly. We also want to make access to the resources widespread. And in order to do that, we have borrowed a concept developed by a colleague at YASA, Narasimha Rao, with his colleagues, and this concept is called decent standards of living. Now, this is a normative input assumption to our scenario. The scenario postulates that we want to have every citizen on the planet to have at least decent standards of living. So, you know, this is a traditional problem in the access literature and poverty literature. Okay, we are fine to understand what does it mean to escape poverty and to get access to energy, but what's the next step? So this is a way of trying to operationalize the next steps, and that's the quantitative framework: minimum food intake, minimum shelter, minimum amount of consumer goods, a minimum amount of personal mobility in terms of passenger kilometers, and then we calculate an induced final energy demand from this. And as you see, our scenario far exceeds even the decent standards of living thresholds. So we can provide 30 square meters of floor space for every citizen on the planet in this scenario, under the assumption that the buildings are very energy efficient. Okay? We can supply 3,000 calories per capita per day under the assumption that we minimize food waste. Yes?
To clarify, so these projections obviously depend on population. So what sort of growth rate for population did you assume?
This is a typically intermediary population scenario. I'm not postulating any particular. We have always used for population and GDP projection both SSP1 and SSP2. These are two IPCC scenarios. SSP1 is more audacious in terms of transitions. SSP2 is more conservative, more middle of the road. These numbers can be satisfied for both population and GDP scenarios, both in SSP1 and SSP2. I do not want to discuss SSP3. You know, a fragmented world is not a world in which we can have a global perspective on sustainable development and equitable access. So it's a contradiction by itself. So both populations are consistent, okay? So that's the scenario. I run out of time, so basically just let me walk you through the highlights. This scenario provides higher level of energy services than even the highest scenario from the Global Energy Assessment. So it is a very affluent world in terms of energy services. But it is a very frugal world in terms of energy use. Our projected energy use by the year 2050 globally is less than 250 exajoules. This is significantly below the actual use of energy. So this is a scenario in which we postulate an efficiency-driven peak energy. And the peak energy is 2020. That's what the scenario postulates. This allows us to have rapid transformations in end use and in supply. And these rapid transformations allow us to stay below 1.5 degrees global mean temperature change, which is an exceedingly ambitious climate target. And we do not require any negative emission hocus pocus. So we can do it with existing technologies. And best of it all, or the entry point of it all, is we don't do it because of climate change. We do it because we want to have sustainable development. And actually, this scenario is extremely, it's best performing on 6 dimensions of the SDGs, as I will illustrate. So that's how this scenario looks like. That's the energy demand in this scenario. It's even lower than the most audacious Greenpeace scenario ever published. And you see how it compares with the literature range of 1.5 degree scenarios. On the top panel, you have the structural change in the sectorial composition of energy demand. Here you have the final energy demand by fuel. You see that this scenario postulates a very rapid electrification and move into a hydrogen economy, so what the Japanese refer to as hydricity. And this structural change allows us to scale up smaller scale renewable electricity and other supply options, also rapidly leading to rapid decarbonization in the system. This is a trend both in the north and in the south. Also, of course, the peak energy is much more pronounced in the north. So you see that compared to today, the energy demand in the OECD countries in this scenario by 2050 is supposed to be halved. Okay? We're here at 180 exajoules today, 2015, and that's the value for 2050. For the developing countries, we're supposed to move from 200 exajoules today down to approximately 155 exajoules. It's a challenge, but it's thinkable.
Just clarification, what's the second, the green bar on the top, the non-energy use?
The green bar on the top.
On the top panel.
This.
In the top panel.
The green part, non-energy use. That's energy use for feedstocks, so where we do not burn the energy for oxidizing it into CO2 for energy purposes, but we use it, let's say, for plastics, lubricants, and other specialty materials. So it's a raw resource, very difficult to substitute, and so therefore it's important to keep a separate track of it. It's not a dominant category, but because of the limits of substitutability, we have quite some concerns, and we need to think carefully about it, and so we have included in the models. Okay, so what is the outcome in terms of climate change? This is the result of the scenario run through a probabilistic magic model setup, and you see that we have a peak in the warming signal around 1.5 degrees by the year 2050 and a consequent decline. And we can assure this peak with at least 50% probability. It's actually slightly above 50% probability. So we can really stay below 1.5 in this scenario. And the key to this success is the exceedingly low demand and the rapid structural transition this low demand actually requires. Now, to the SDGs, we have looked at hunger, health, energy, climate, and oceans and land. The desirable direction on these SDGs is always indicated by the blue arrow. Sometimes we want to go up, sometimes we want to go down, depending on the indicator. And here you see the green low demand scenario in comparison to the traditional IPCC SSP scenarios for 2.6 and 1.9 watts per square meter. So 2.6 is approximately 2 degrees warming, and 1.9 watts per square meter radiative forcing change is the 1.5 degree target. And as you can see easily, the green scenario is at least as good as the best SSP scenario, and in many cases better for sustainable development. So the improvements on the sustainable development dimensions are so significant that we no longer can speak of SDG co-benefits. We speak of the SDG benefits of this scenario, and the climate change, that it stays below 1.5, is a co-benefit. But the real benefit is actually in the conservation of land, in the provision of food in ending hunger, in the significant reduction of air pollution that improves human health, in meeting the energy goals of the SDGs. By 2030, no use of traditional biomass anymore. Everybody has access to clean cooking fuels. And that's doable within 10 years. We can prove it. Of course, it requires political will, it requires policy interventions, but we can do it. Have zero carbon electricity supply in India over 10 years, we also know that we cannot do this either in 10 years. It's a long-term project. But energy access we can fix. So that's where we have zero traditional biomass use in this scenario. We are right on the 1.5 degree target. We have significant benefits in terms of minimizing ocean acidification, because we do not have this overshoot and the interim accumulation of CO2 in the oceans, because we have a different emission profile. And we are also very efficient in terms of using land and restoring land to nature. And so we also are very good on SDG 15 in terms of land. So a very different perspective on long-term transitions, starting on efficiency improvements in existing systems, changing end-use technologies and services with an emphasis on service efficiency, focus on granular and distributed options, and all of that with the objective to maximize the SDG benefits, having climate change as a co-benefit. So, the overarching narrative is simple. It has been given to us by SDG 12. We just didn't know it. Somehow, unwittingly, perhaps the people that negotiated SDG 12 didn't have that in mind, but we are thankful nonetheless that we now have a narrative of how we can illustrate what does it mean, responsible production and consumption. And the key point is it starts with responsible consumption, and that will enforce responsible production. This is a very contrasting scenario to the traditional approach, where we basically assume business as usual demand and consumption growth, unabated consumption growth. As a result, we need large-scale supply-side options, and we need climate fixes, either through negative emission technologies or, horribile dictu, ultimately through geoengineering. So these are the two most contrasting alternatives. I see very limited SDG co-benefits of this, but I see a lot of climate co-benefits in true sustainable development, which starts with responsible consumption through efficiency and end-use changes. So thank you very much for your attention, and I look forward to our discussions.